Okay, guys, today is part two in our series on talking about stellar evolution, and we're going to try to tackle questions 18 through 24 in our packets. So you can have those open. Uh, let's kind of do a little quick refresher here. Last time we left off, we were talking about degenerate matter and how it's a little bit different than regular matter. Uh, and we're looking at fusion inside the stars to see kind of how this is all going to play out. So let's take a glance here at some helium fusion. It's really similar to hydrogen fusion. There's only some differences, particularly in how much the particles want to repel each other. So in this scenario, we've got two helium nuclei that are going to collide with enough temperature, pressure, and momentum that they can basically stick together, that the strong nuclear force can take over and create a beryllium. So the two helium nuclei are on the left side of the diagram there, and you can see that it's helium 4, so they've got four subatomic particles there, two protons, two neutrons. Protons, remember, have a positive charge, and positive charges, like charges, don't like to be near each other, so they repel. In order to stick those two heliums together, there is going to be required a lot more energy put into that to slam them together enough to force them to get close enough that the strong nuclear force can take over and bond them together. And that's just because right now we're dealing with four positively charged things rather than just two when we were talking about the hydrogen nuclei colliding. So anyway, it's a bigger barrier for fusion to get over, but a star can do that once it develops enough temperature and enough pressure. So through a series of reactions and releasing radiation in the form of gamma rays, we then create carbon 12. So as the star becomes a giant, it's fusing hydrogen in a shell, and the helium core contracts, heats, and can even become degenerate. Helium fusion requires a lot of heat, right? So I said here it's 1 times 10 to the 8 kelvins to ignite helium fusion. Okay, so what's going to happen with this helium ignition? So not all stars can undergo what's known as a helium flash. So that's the answer there to number 18. It's only stars that have a mass somewhere between 0.8 and 2 solar masses. And I wrote there that they don't ignite their helium gradually. In other words, they ignite in a flash. It's a pretty big moment. So what's going on with stars that are a little bit bigger and a little bit smaller is that if they're a little smaller, they never get hot enough to ignite their helium. Okay, if they're a little bit bigger than that, they'll ignite their helium before it ever becomes degenerate. So it's just kind of like a gradual ignition process, and then they kind of go on about their stellar evolution. But I want to talk about those ones that fall in that 0.8 to 2 range because that's the interesting part. They don't ignite gradually. Their helium does become degenerate. And remember, to understand this whole thing, you've got to understand that in degenerate matter, pressure doesn't depend on temperature. So you can make it as hot as you can make it, it will not create any more pressure down there in the degenerate matter to help support the star. So when the helium ignites in this degenerate matter, it just has to ignite in one small tiny region, and the temperatures are going to soar. Because remember, degenerate matter is an excellent conductor of thermal energy, of heat, and it's not going to create any extra pressure through this. What's going to occur is all that helium is going to heat up like instantaneously, and basically take off in a runaway thermonuclear explosion and ignite all of the helium like virtually at once down there in the core. It's such a powerful explosion that it's able to lift the outer layers of the star out away from it for a couple of hours before it settles back down. So it's a pretty big explosion. Now, if we saw one of these things without the outer layers of gas around the star, it would be brighter than an entire galaxy. So it's a pretty big explosion. However, the star has a lot of gas covering it up, so it's hidden down deep inside. So other than the layers lifting out and then the star settling back down, we don't get to see a lot from one of these helium flashes. Now, after it does this, what's interesting in the pictures I put there, is that it can seriously mix the interior of the star up. It can really mix, kind of convect those gases around, and actually change how the star develops later on, because it can basically bring more hydrogen down into the depths of the star for fusion. But anyway, that's what occurs during a helium flash. Let's see here if we've done our question. So, describe the cause and process of a helium flash there for number 19. The causes of this are essentially the matter becoming degenerate down in the core of the star, right? And then all of the helium igniting at once in a thermonuclear explosion. That's essentially what causes the helium flash. Okay, here we go. So after the helium flash, stars move over to what we call the horizontal branch of the HR diagram. So don't get too hung up on all these drawings. I'm just showing you this because you're going to see this again later on, and it will hopefully make a little bit more sense when we use one of these things. But you can see the main sequence there. It's on the main sequence when it's fusing hydrogen into helium. When it runs out of hydrogen, a star leaves the main sequence and starts to track up towards the red giant branch. As it becomes a red giant, it's now building up all this helium ash in its core, and it becomes degenerate. If it does, it will ignite in a helium flash. And then what's interesting is it moves suddenly back towards the main sequence. Now remember, the star is not physically moving through space, right? It's just moving on our diagram. So think about what's causing it to go back to the main sequence is the fact that once it ignites that helium, the temperature and the pressure thermostat of the star can kind of take back over. In other words, pressure and gravity balance each other, and the star moves back towards the main sequence as though it was like just starting its life again, right? So if we kind of think through the process here, we're going to walk sort of through the whole thing. But at first, it's helium's fusing in the core, fuses to carbon in the core, and carbon accumulates in the core, and hydrogen's going to be fusing to helium in a shell outside of the core. It's going to start to make this whole thing look like an onion when we're done. The star is, of course, going to get smaller and hotter as it does that, and that's part of why it slides over on the main sequence, back towards the main sequence. Okay, let's move forward here. Okay, when we look at the structure of a star that's going through this whole process, the hydrogen was being fused into helium, okay? The helium's now going to be fused into carbon and oxygen, and that stuff's what's going to build up in the core now as ash. So remember back when we were fusing hydrogen, we were building up helium ash. Now that we're fusing helium, we're building up carbon and oxygen ash. So that's your answer there to number 20. The elements that are going to form the ash from the helium fusion are going to be oxygen and carbon. Those are going to build up. Now, think about those two elements for a second. They're pretty darn important to life, right? We are made out of carbon, and we really like this oxygen stuff to breathe. So both of those elements are extraordinarily important. They're formed down in the depths of a star. In fact, in the depths of a regular old main sequence star, like our sun, smaller mass star. When we say things like, you are made of stardust, like literally, you are made of stardust. The stuff that makes you up, the carbon that makes your body up, the oxygen that you breathe comes from stars. And this is exactly how it's happening right here. So we've got carbon and oxygen ash building up in the core. Fusion is going to slow, pressure will decrease, and the star is going to contract, right? Igniting a helium fusion shell. So don't get too hung up on all of this, but we're going to end up with layer after layer of different fusion processes taking place, and each one's going to use the product or the remnants, the ash from the one that's above it. So we're going to be consuming what's in the shell above as we go through this. Okay, let's see where we're at on the paper here. Oh, good. So we've answered number 20, the elements that form from helium fusion. So while this is going on, the helium is going to run out in the core, right? And a helium shell is going to begin to fuse right beneath the hydrogen fusion shell. And the carbon core is likely to become electron degenerate as the star swells up. So once again, pressure is no longer going to depend on temperature, and the star is going to kind of go through this funny zigzaggy pattern on the HR diagram. So it started on the main sequence, ran out of hydrogen in its core, started building up helium in its core, swells up, and it moves up towards the red giant stage. Then once it ignites a helium flash, if it does, it's going to drop back down towards the main sequence and kind of look like it's moving back onto the main sequence because pressure and temperature are going to balance back out again for a while. And for a while, it'll be stable. It will take, for instance, for the sun, about 200 million years to go from the main sequence all the way to the top of the red giant branch. Now, for a star, that is like really quick. Remember, our sun is going to take 10 billion years on the main sequence. 10 billion as compared to just 200 million to go when it leaves the main sequence all the way up to the top of the red giant. So once it gets up there to the top of the red giant, our star will sit there for about another 100 million years fusing helium into a non-degenerate carbon core. Okay, so it won't necessarily make a degenerate carbon core. It needs to be big enough to do that. So they won't all go through that. For our star, and for a lot of lower mass stars, they won't be able to ignite the carbon that's in their core. Like that will be the end. So before the temperature and pressure gets high enough for the carbon to ignite, the star starts to lose mass. In other words, it starts to get so hot and swell that it starts to actually blow away its outer layers. And remember, this is kind of like a runaway effect here. The more mass you lose, the less gravity you have to hold on to your mass, so the more mass you lose. So a failure to ignite carbon can lead to a tremendous loss of mass, and a star can just blow off all of its outer layers for the most part. So these outer layers eject out into space in that time, and the star rapidly shrinks, becoming hotter, and this causes it to move across the HR diagram down and back towards the bottom right of the diagram. So it'll move to the left and then back to the right. So it's become, as far as we're concerned, much less luminous. Its surface temperature has changed quite a bit, right? Its surface temperature has actually increased. If you look at the diagram there, compared to the red giant stage, and now it's a white dwarf. So what's gone on during all this? Well, if the right conditions prevail and the star is able to eject a bunch of mass, a bunch of its atmosphere, as it becomes a white dwarf, the white dwarf will emit tremendous amounts of ultraviolet radiation. And that radiation will light up that cloud of gas and dust that the star gave off when it became a white dwarf, and we'll have this beautiful planetary nebula afterwards. So we'll take a look at a couple of pictures of those here. Here we go. So I've got a nice little description here for you of a planetary nebula, so you can go ahead and answer number 21 there, the causes of a planetary nebula. Okay, and here's some photos of them. We've got the Eskimo Nebula up there, the Cat's Eye, the Helix, some of the most beautiful ones in the sky. And these really are gorgeous remnants of stellar deaths out there. So if you look very close, in some of them you can actually see, like in the Eskimo, you can see the central star there, the white dwarf that's down deep inside. That thing's emitting a bunch of ultraviolet radiation that's actually heating up that cloud of gas that's been blown off. So what causes a white dwarf? So we've ended up with a star that's blown off its outer layers, and it's heating those layers up, and it might last that way for like another 50,000 years before the gas expands too far away and disperses, and it goes away. So these are kind of brief instances in star life here. Planetary nebula has nothing to do with a planet, by the way, right? Okay, white dwarf, size, density is made up of. Let's take a look at those here. Here we go. So let's describe a white dwarf, its size, its density, what it's made up of here for number 22. What a white dwarf is the leftover core of a star, okay, that's become an electron degenerate carbon core. So the carbon is packed as tightly together as can possibly be packed. Its electrons are as close as they'll go. This is where you've probably heard before people saying poetic things like, there's stars that are composed of diamonds. We're talking about carbon that is compressed into something that is not even close to a diamond. It's way more tightly packed than that. This thing is the size of the Earth. So if you think about this, they're anywhere from 0.6 to 1.4, almost 1.5 times the mass of our Earth. But this thing is tiny. It is really crushed in there. A teaspoon of this stuff has the density of a ton. So could you stand on the surface of a white dwarf? Oh, there's no way. You would be, first of all, as you got close, you'd be instantly like melted because the radiation that they're giving off. But if you got anywhere near the surface, you'd just be smushed, right? There's tremendous gravitational force on something that's that massive, crushed into the size of the Earth. So they're really hot, but they're not very bright, not very luminous at all, because they're just so tiny. So surface temperatures on the white dwarf are somewhere around like 100,000 Kelvin. They're emitting a lot of UV light, and that's why they're ionizing that planetary nebula. Right? Now, this is kind of a fun time to maybe talk about what's going to happen to the white dwarf, because the white dwarf is not really the final stage here. So the star went through this process of being a main sequence, moving off, becoming a giant, and then, of course, collapsing into a white dwarf, blowing off its outer layers, which became the planetary nebula. And then the white dwarf is going to exist for a really long time. Eventually, a white dwarf will cool off to where we can't see it anymore. It doesn't emit any light that we can easily detect. And at that point, we've decided to call them black dwarfs. So we've got white dwarfs, we've got black dwarfs, we've got red dwarfs. It's turned into the land of the hobbits in here. So a black dwarf is entirely theoretical. And the reason it's theoretical is because it would take longer than the age of the universe for a white dwarf that formed at the very beginning of the universe to have actually cooled off to become a black dwarf. Think about that for a second. The universe isn't old enough for the very first stars, if they became white dwarfs, to have cooled off to the point where they're dark now. So the universe is pretty old, but it's got a long ways to go. There's a lot of stuff that's going to happen in our universe before it's all said and done. What's interesting, though, is that those white dwarfs, because we know how long they should take to cool off, because we understand the physics, that actually kind of puts a limit on the upper age of the universe, right? If we don't see any of those, if we can't detect any of them, we can take a look at what the coolest white dwarfs are, how cool they've gotten, and we can kind of extrapolate backwards to figure out how long has that dwarf been here. Well, the universe can't be younger than that, right? So it's kind of interesting. Anyway, where are we at here on our we're going to list the stages of evolution of our sun. Hold off on that for just a second. Number 23, we're going to talk through all of that, and then I will simplify it for you real quick. So as we go on from here, let's say a star is larger than the sun, considerably larger than the sun. It's going to be able to fuse heavier elements. It's going to have enough gravitational force to crush its core to the point where carbon, oxygen ignite. Okay? Once those things start to fuse, you end up with crazy complex sets of reactions. I just threw this one up here for you. You can see everything from magnesium, sodium, neon, aluminum, oxygen, carbon, nitrogen, all those things forming through just one one reaction, nuclear reaction that takes place inside the star. And these get very complicated. But what I want you to understand is that as the stars transform, they start to fuse different things. Virtually every element that we have in the universe. So as this process occurs, the star starts to look like a giant onion. And this is not to scale at all. But what starts to happen is in the core, it starts to develop iron and nickel. Those things build up in the core, very heavy elements, right? They're some of the latter products of fusion. We've got silicon outside of that. We've got oxygen, neon, magnesium, oxygen, carbon. Each shell is fusing something that's making ash that's falling to the shell beneath it, which is fusing into something that's becoming ash for the shell beneath it. So it's this really interesting process where the star is burning, if you will, from the center outwards, and each layer is making the stuff that the next layer down needs to burn. Now, eventually, every star is going to run out of fuel. Every star is going to succumb to gravity. In the end, gravity always wins, right? And some of these giant stars are going to go out with a real big bang. And we'll talk about that later, big supernova explosions that are going to give us neutron stars, black holes, some really bizarre objects in space. So anyway, let's kind of wrap that all up here, and we'll list number 23, what the stages of evolution are for our sun. So take a look at this diagram. If you look over on the left there, left-hand side, you've got a sun-like star. So if we want to walk through the diagram, you start out with a protostar. Right? It's a cloud of gas and dust that contracts, starts fusion. Once fusion ignites, it's on the main sequence. So that sun-like star picture there, that's our star on the main sequence. It's on the main sequence. It's fusing hydrogen into helium. That's where it's going to spend the majority of its life. So that's why the longer arrow there. It's got longer time on the main sequence. When it runs out of hydrogen to fuse in its core, it's going to swell into a red giant. Okay, this is where the life of the star starts to progress very rapidly. Once it swells into a giant, for a star the size of our sun, its end state is going to be a white dwarf. Right? And as it forms a white dwarf, it's going to give off, more than likely, a planetary nebula. Okay, those gases are going to be ejected and heated up, and they're going to glow like neon lights in the sky and be a beautiful object out in space. So you can disregard there where it says type 1a supernovae. That's something that can happen in a binary star system. We'll talk about that a little later. But our star is going to end up here at the white dwarf phase. And I guess you could go out one further and say black dwarf. So that'll be the end state for our star. So once again, protostar to main sequence star to red giant to planetary nebula / white dwarf to black dwarf. And that's the life cycle of our star. Now, if you look up a little bit higher there on the diagram, up at the top, you'll see that some of these stars move on to the main sequence from being protostars as what we call blue supergiants. So these are really big, bright blue stars. They're on the main sequence. They're fusing hydrogen just like our star is. And they don't live very long, though, right? They're so big, they burn up all their fuel. These guys could become black holes, neutron stars. They're going to become some of the interesting things that are out in the universe. And on the far other end of the spectrum, we talked about these already, these little brown dwarfs that are not even hot enough to really become a star, right? They're just like big, hot planets that are almost stars. So they just kind of always stay cool brown dwarfs. They don't ignite fusion. Okay, that's there for number 23. Let's wrap up here with some star clusters. So a star cluster, we've got two parts to this question here for number 24. What is a star cluster and what clusters help us to understand? So let's get both parts. First of all, simply put, a star cluster is a group of stars that all formed at the same time. So they're all born at the same time. The reason this is important to us is because these things allow us to see the evolution of stars. None of us lives long enough as humans, or has lived long enough as humans, the entire human race, to see a star go through every part of its life cycle, right? So even a large star, think about our sun. Right? If you're going to watch it from start to end, we're talking well over 10 billion years. That's a long time to watch a star go through its life. So to figure out how stars evolve, we actually look at clusters. They all started at the same time. We can see what happened to the biggest ones. We can see what's happened to the smallest ones. We can see some in some other clusters that are just forming. So what the star clusters allow us to do is to see how stars actually evolve, right? This is a picture of the Pleiades. It's a beautiful photo. Remember, you should go out and take a look at the Pleiades maybe tonight if it's clear out. And if you can see what I think 7 stars, your vision's pretty good, right? It's an ancient test to see how good your vision is. I think this slide here is just the last thing that I just said here. So in answer to number 24, right, trying to figure out how stars evolve, we only really see a momentary glimpse of the universe. So a cluster gives us a snapshot of all the stages in the life cycle of the star. You've got some that were big, some that were small, some that were in between. How have they evolved in the time since the cluster formed? And that allows us to kind of unscramble all those stages of the star to put together the HR diagram to understand how stars evolve. And that's really the only way we'll unravel that mystery. So you guys have a good day. Until next time, I will see you later.